Alright guys, this video is showing you how to handle a kinematics problem in which there are multiple accelerations. For starters, to figure out whether or not there are multiple accelerations, I should have started this video with a marker, there's one, kind of comes from the context and your understanding of acceleration. For example, if I were to throw this marker up in the air, okay, I know that there's an acceleration caused by gravity the entire time it's up in the air. But there would be a different acceleration caused to go from 0 to some positive value by my hand, and then there'd be a third acceleration when it came down and hit my hand. Now I could probably guess that the first and the third are probably going to be the same, but you can see this probably easily with signs. So for example, there's a homework problem that does something like there's a traveling vehicle and it speeds up. Okay, so of course this means it's going to accelerate. It's increasing its velocity. Or acceleration is forward in that. That's why velocity gets bigger and bigger and bigger and bigger and bigger and bigger. Okay. Then if it were to say, for example, go to a constant velocity, okay, well this means acceleration goes away. We would consider a zero acceleration a new acceleration for that particular instance. So that would be its own section. Acceleration would be 0. And specifically with the 0 acceleration, well then it would be a constant velocity problem. Right there. We'll see like one of those here in just a second. If this is an acceleration that's positive. If the vehicle then, after a certain amount of time of traveling with the 0 acceleration, constant velocity, hit the brakes, well then for this particular section over here, acceleration would be negative. Velocity going this way, acceleration going back the negative way to decrease that particular velocity. So the important thing in figuring out whether or not there are multiple accelerations is your understanding of what acceleration specifically means. So let's look at a situation here. Let's say that Spainhour is running, okay, down the hallway at max speed. Okay, max speed. It doesn't have to be Spainhour, by the way. I don't have to be self-congratulatory or focus on me. It's somebody else. It's Kyle. Kyle's running somewhere. I don't know. Kyle's going to be traveling at 8 miles an hour. Okay? And, nope, take that back. He's not traveling 8 miles an hour. Where is he? You never know with Kyle. Let's say Kyle travels, something like 7 meters. Okay? And it takes him to travel that 7 meters. It takes him 3 seconds. Then, unfortunately, Kyle was not looking where he was going, and he runs into an elephant. Okay, an elephant. Nailed it. Look at there. Elephant. Perfect. He runs into an elephant. All right, and the elephant stops Kyle in, I don't know, 0.3 seconds. And what we want to know is when the elephant stops Kyle, how far did Kyle go? Okay? How far during this particular time? Okay, so when you're setting this up, like I said, there's really not like a great obvious thing for this, but you're going to have to see, all right, if he was traveling at max speed, this means he was at a constant velocity, and therefore his acceleration was 0 meters per second squared. Okay. Then when he hits, so he has some velocity here, okay, and it's not changing. That arrow is staying the same speed. That's why acceleration is 0. No change over time. Then he runs into the elephant, and that acceleration then decreases. Okay, so acceleration is pointed back in this direction over here once he hits the elephant. So this means there are 2 separate accelerations. And again, we do count a 0 acceleration as being a different acceleration, which means we need a different set of variables. Now over here with this acceleration, I'm going to write my set of kinematic variables. Oops. Okay. When it comes to a constant velocity or 0 acceleration, I really only need 3 variables, and that is those right there. This can easily be seen by the fact that the equation at constant velocity is displacement equals velocity times time. So now I can start to plug my numbers in. When he was traveling at constant velocity, he had a displacement of 7. Oh, I got ahead of myself. It can be helpful here to make sure and put subscripts on stuff so I don't accidentally confuse them. This delta x is not the same as that delta x. This delta t not the same as that delta t. So I could put subscripts easily like 1, okay, and 2 over here, okay. I could also, use subscripts like max speed, so I could write velocity ms or something like that, or delta t ms, I don't know, or just Kyle, I suppose. But yeah, Kyle's is going to change, so Kyle isn't necessarily the best subscript for that. Yeah, so delta x1 is 7 meters. Delta t1 is 3 seconds. And I like to finish all of my given and find before finishing, okay? Over here we say the elephant is going to stop Kyle, which means velocity final is 0. And it tells us that he's going to stop in 0.3 seconds. The difference between the delta t's is that this is how long he's traveling at that constant speed, and that over there is how long it takes him to specifically stop once he hits the elephant. Okay? Now, what you'll notice over here is we only have 2 variables, and over there we only have 2 variables. Now, in this particular case, that's okay, because the equation's only made out of 3, so we can find anything we need in there. Over here, we only have 2 variables. Since it's accelerating, though, we know that we actually need 3. So we're going to have to find something in between. Well, if I understand my situation correctly, okay, this set of variables is describing from here to here, the amount of time it takes to go from there to there, displacement from there to there, and the velocity therein. This set of variables describes this section right here. So we're trying to figure out how far it takes the elephant to stop him. Now that's important to know because this 0.3 is during this time, the acceleration is during that time, the final velocity is there, and the initial velocity is right here. So the initial velocity of that set is just going to be whatever velocity he was traveling at. So I can use this set of variables to simply find how fast he was going. 7 meters in 3 seconds means what? 2.33 meters per second. I come over here, I punch in 2.33 meters per second, and I just find the equation that has those 3 variables and what it is that I'm specifically trying to find. That's going to be this guy. And let's do our algebra and solve for it. Velocity final is 0. I like to plug my zeros in early. And we're trying to isolate delta x. Oh, good, we're all set. So delta x is equal to velocity initial, 2.33 meters per second, all over 2, times a time of 0.3 seconds. So let's go ahead and punch that in. I'm going to go ahead and check my time over here to make sure I was correct. Yep, got that right. Divided by 2 times 0.3 is 0.35 meters, or about 35 centimeters. And maybe that doesn't make full sense to you. Like, wait a minute, what do you mean he traveled that far? So he collided with the elephant's tuchus, okay? And that means he traveled 35 centimeters into the elephant. Now, either one, there's a lot of cushion in that elephant, which is, I don't think actually accurate. I think they're probably pretty solid. Or it means I, just making up a number, probably got a number wrong. That number that I'm guessing that I got wrong, which led to that 35 centimeters or 0.35 meters, is probably this time right here. I probably overestimated how much time it actually takes. We've also done the opposite. We could have said, let's say that the elephant only gives about 10 centimeters, okay, during that time. We could have plugged in the 10 centimeters and figured out either A, how much time he would stop, or B, the other thing that we could calculate here is how much acceleration is during that. That's always an interesting one. Like how much acceleration, how does that compare to gravity? We could do that real quick. If the problem had asked acceleration is just equal to change in velocity over change in time, this, of course, you could also get acceleration. These are the same thing. You'll see me regularly go to this definition of acceleration now. Change in velocity went from 2.3 down to 0, so that's just negative 2.33 meters per second. It stopped in 0.3 seconds. So the acceleration, yeah, that acceleration is way too small, is negative 7.7 0.78 meters per second squared. Yeah, that elephant's tuchus would definitely cause way more acceleration than that. So I will off with the numbers, but this is how you do that problem. This kind of conversation at the end here is kind of one that you always sort of have to have is, does that answer make sense? But that's how to do a problem with multiple accelerations.